Hello everyone, welcome back to Exam Ignite. In this video, I will continue the Module 4, Part 2 of the Principles of Communication System based on the VTU syllabus 2022 scheme. We have already completed the Part 1 and you have not watched it. You can find the link in the description box below. Like I have always said, this is an handwritten notes that is made easy to understand by referring the model question papers and the VTU exam papers that 2025 and July 2024 papers, Jan 2025 and July 2024 papers, so that it is an exam focused notes. So all those questions are covered in this. So go through the complete video so you can understand easily and learn quickly. So let's get started. Quantization process, the process of transforming the sampled amplitude, that is m of nts, of a message signal, that is m of t, into a discrete amplitude, that is v of nts levels, is referred to as a quantization. Continuous samples are given into the m, that is given into a quantizer, and we get the discrete sample v. Quantization can be uniform or non-uniform. The quantizer characteristics can be mid-thread or mid-rise type. That is, mid-thread is given like this. Here you can observe the difference, and for the mid-rise, here you can observe the difference. Quantization noise. The use of the quantization introduces an error defined as a difference between the input signal M and the output signal V. This error is called as a quantization noise. Let the quantization error be denoted by a random variable q of the sample value small q. We may thus write it as q is equal to m minus v, or capital Q is equal to capital M minus v. So this figure illustrates a typical variation of the quantization noise as a function of time, assuming the use of a uniform quantizer of the mid-thread type. It is of mid-thread type. So here this is our magnitude input signal, that is our x into nts. This is our quantized signal, and this is the error we can observe here. This is an illustration of a quantization process and the noise. This is a waveform magnitude versus time. Consider then an input of m of continuous amplitude in the range of minus uh, m maximum to the m maximum. Then the step size of the quantizer is given by delta is equal to 2m maximum by L. Consider that as equation 2, where our L is what? Total number of representation levels. Now the probability density function of the quantization error, that is Q, it is given by this. Now the variance of the quantization error is given by sigma q square. So we will substitute fq is equal to 1 by delta. So we get this equation. Finally, apply the limits, take the integration, apply the limits. After applying, substitute it. So substituting and cancelling and solving, we get sigma square q is equal to delta square divided by 12. Consider this third equation. This is known as the mean squared quantization error or the normalized noise power. So quantization error in terms of power. Let us consider R with a denote the number of bits per sample. Then the quantization level is given as L is equal to 2 power R. So substitute this 4 in our equation 2 that we had considered previously. That is this equation, you have to substitute the L. What do you get is 2 m max divided by 2 power R. Now substitute this fifth equation in our equation 3, that is sigma square q. So on substituting and taking the square of that and taking the reciprocal and solving, you get this sixth equation. Let here our P be the average power of the message signal m of t. We may express the output signal to the noise ratio of the uniform quantizer as SNR ratio, that is P by sigma square q. Substitute the sigma q square and take the reciprocal, you will get the equation 7. This shows the output signal to noise ratio if the quantizer increases exponentially with increasing number of bits per sample, that is R. Next is pulse code modulation, PCM, important topic. The pulse code modulation is a message signal. It is represented by a sequence of code pulses which is accomplished by representing the signal in the discrete form in both time and amplitude. So the basic operation performed in the transmitter of a PCM system are, we have sampling, quantization and encoding as shown in figure 8, that is this figure. Next, the low-pass filter prior to the sampling is included to prevent the aliasing of the message signal. The quantizing and the encoding operations are usually performed in the same circuit, that is, which is called analog to digital converter, ADC. The basic operations is the receiver are generating the impaired signals, decoding and reconstructing of the train of quantized samples as shown in C. I'll show it down. So the regeneration also occurs in the immediate points along the position path as necessary. So you can observe here, this is the transmitter, the source of continuous time signal. It is given to low pass filter, then to sampler, quantizer, encoder, we get the PCM signal which is applied to channel input. So now we will give that to our channel input. So that is sent to regenerative repeater, many repeaters. So we get a regenerated PCM signal which is applied to the next part, that is our receiver part. So final channel output is given. Then we have a regeneration circuit, we have decoder that is sent to the reconstruction filter. Finally, we get the destination. It is a receiver part. These are the basic elements of the PCM. You need to explain these 3 steps when it is asked in case of PCM. Sampling. Next, you may get a definition to answer, or you have to explain the sampling, quantization, encoding. So the incoming message signal is sampled with a train of narrow rectangular pulses as to closely approximate the instantaneous sampling process. In order to ensure there is a perfect reconstruction of the message signal at the receiver, the sampling rate must be greater than the sampling rate. You have to notice it must be greater than or equal to the highest frequency component, that is omega, of the message signal in accordance with the sampling theorem. We have already learnt this. Fs is greater than or equal to 2 omega. Now comes quantization. Here the sampled version of that message signal is then quantized, thereby providing a new representation. That is what discrete in both the time and the amplitude. We are having uniform and non-uniform. Uniform means we have a mid-thread and mid-rise quantization for the uniform. Mid-thread and mid-rise. For the non-uniform, we have compressed loss, that is mu low. The use of this non-uniform quantizer is equivalent to the passing the baseband signal through the compressor and then applying a compressed signal to this uniform quantizer. The particular form of compressing the law that is used is practice is called as mu law. So mu law is defined by the log of 1 plus mu by modulation of m divided by log of 1 plus mu, where our m and v are the normalized input and output voltages, where mu is a positive constant. You can observe the graph here, which is normalized input M versus the normalized output V. Then normalized output V versus the normalized input M. This is for our mu 100, mu 5 and mu 0. This is for A1, A2 and A100. So another compressor law is used in practice, that is we call A law. That is what here I said. This is about for the mu law and this is for the A law. So where our V is defined as A by modulation of M divided by 1 plus log A till 1 plus log of A modulation M divided by 1 plus log A with their limits. Now encoding. This is in combining the process of the sampling and quantizing, the specification of the continuous message signal becomes limited to a discrete set of value, but not in the form of best suited to transmission over a line or radio path. In a binary code, each symbol may be either of 2 discrete values or kinds, such as the presence or absence of a pulse. The 2 symbols of a binary code are denoted as zeros and ones. Line codes, important part, they may almost the 90% chances asking on this topic is they will give you the value, that is they will give you the binary numbers like this and you have to draw the waveform for that based on the whether it is types of line codes. So it is a line code that has a binary stream of data, takes on an electrical representation. We are having 5 line codes. First one is unipolar non-return zero, that is called as NRZ signaling. In this, the line code symbol 1 is represented by transmitting a pulse amplitude A, and a symbol 0 is represented by switching it 0. You can observe here, for the 0 it is down, for the 1 it is up, again 1 up, 0. It goes on like this. This is called NRZ. Next comes the polar NRZ, that is polar non-return to 0 NRZ. In this, the line codes symbol 1 and 0 are represented by transmitting the pulses of amplitude, that is plus A and minus A respectively. So here 0 is there, it is at 0. When it is at 1, it goes to the plus A, and when it is 0, it is from the minus. You can observe here it is minus A to plus A here, but it is here only 0 to plus A. Same again for the minus 0, it comes to minus A, 1 means it goes to plus A. We are having it is the minus A to plus A, here it's from 0 to, as it is non-return to 0, this is non-return to 0. Next comes is unipolar return to 0 signaling. Here, symbol 1 is represented by a rectangular pulse of amplitude A, that is half symbol width, and 0 is represented by transmitting no pulse. You can observe here in the third waveform, this is our 0. Now for the 1, it goes into halfway and get back to 0. Then again for the 1, it goes to halfway and get back to 0. For the 0, it is in the 0 itself, and for the 1, it goes to halfway and get back to 0. For the 0, it continues to be 0, and again 1, it goes only halfway, half symbol width. Next is bipolar return to 0, that is BIZ signaling. This line code uses 3 amplitude levels. That is, I'll show specifically positive and negative of the equal amplitude, or alternatively for the symbol 1 and 0. No pulses. The line code is called as an alternate mark inversion, you can say AMI signaling. So this is here, this is our 0, it remains in the 0. When it has 1, it goes a halfway and it will return to 0. For the next one, it will go in the negative direction, halfway, and it returns to 0. Again we have 0, 0. Next for the first, again 1, it goes to the positive half and returns to 0. And again if it gets the next one, it goes to the halfway in the negative direction and returns to 0. So this is what about bipolar return to 0. Next is split phase, that is Manchester code, or you can say split code. Symbol 1 is represented a positive pulse of amplitude A followed by a negative pulse of amplitude A, with both the pulses being half symbol wide. Both are half. For symbol 0, the polarities of the two pulses are received. Here you can observe for the 0, it is halfway. It goes up halfway. Again for the 1, it goes halfway and gets down. Again next is 1. So it goes halfway and returns to 0. Next it goes halfway. It is like, as I said here, 1 is represented with positive pulse of A and followed by the negative pulse of minus A, with both the pulses being half symbol wide. Both are half symbol wide. Okay, next is the differential encoding. Here, this method is used to encode the information in terms of signal transmissions. In particularly, a transmission is used to designate the symbol 0 in the incoming binary data stream, while no transition is used to designate the symbol 1 in the figure. So, origin binary data is our 0, 1, 1, 0. This is what we are having. Differential encoding data, that is, we use an XOR. For it 0, 0, it is 1, 0, 1, it is 0, 1, 0 means 0, 1, 1 means 1. So this is how we do compare it with our, for the 0, 1. For the 0, 1, for the 0, 1, it is 0. Now for the 1, 0, it is 0. For the 1, 0, it is 0. For the 0, 0, it is 1. For the 1, 1, it is 1. Again 0, 1, it is 0. For the 0, 0, 1, 1, 1, 1. So based on that, you have to draw the with the reference bit versus the time. Now next is waveform. It is of that waveform. Next, regeneration. The distorted PCM wave obtained from the transmitter is then sent to the amplifier equalizer. The output of this equalizer device is passed to the decision-making device. To the device, the signal turns 1 or 0 code at output. That is distorted PCM. We'll go to the amplifier equalizer. There to the decision-making device along with the timing circuit, we get the regenerated PCM wave. This is a block diagram representing the regenerative repeater. Last is the decoding. The decoding process involves a regeneration of the pulse amplitude, of which is a linear sum of all the pulses in the code word, with each pulse being weighted by its value, that is 2 power 0, 2 power 1, 2 power 2 till 2 power r minus 1, where our r is a number of bits per sample. Filtering, it is a final operation of the receiver to recover the message signal waveform by passing the decoder output through a low pass reconstruction filter whose cutoff frequency is equal to the message bandwidth. Multiplexing, in the applications of PCM, it is a natural to multiplex a different message signal by the time division, whereas by each source it keeps individually throughout the journey from the transmitter to the receiver. The individuality accounts for the comparative case with which message source may be dropped or reinserted in a time division multiplex system. So this completes the module 4 part 2. I hope the explanation was clear for you. It was a revision and helps you to identify the key exam topics. If you have missed the earlier parts, including the module 1 to module 4 or any part 1, all the links are available in the description box. Go through that. Don't forget to like, share and subscribe to Exam Ignite. Your support helps me to continue my uploading the videos and exam focused videos along with the important questions. Thanks for watching and see you in the next one.